and the layer that people used in transformers. So that's the program for today. But the idea of generative models, what are we aiming at? So the setting, at least for the beginning, will be the same as usual. So we have the data matrix that is n samples in d dimensions. And our goal is to provide a program that generates new axes, so no labels here. We are still in the context of unsupervised or self-supervised learning as last time. And the point will be to produce a new X that has the same properties, ideally comes from the same distribution. So the idea is that there is each sample comes from some distribution, probability distribution of X's that we do not know. We know nothing about it except that we have n samples from it, and we want to, the goal is to sample. The goal is to sample P of X. So in this lecture, we already had a chapter on how do we sample from probability distributions when we actually know the form of the probability distribution. That was the section about Monte Carlo Markov chains. And that's also very commonly done in physics and other sciences, that you have, Boltzmann measure or some kind of Hamiltonian of how your particles interact, and then by the principles of statistical mechanics, all the microstates are explored uniformly, so you want to sample from the corresponding distribution. But in physics, we don't usually, in physics, we usually know the P of X. Here we don't know it. All we know is that we have samples from the P of X. So that's a more challenging task. And how do we go about it? So we will talk about several methods. So one of the methods, so method 1, that is based on autoencoders. So that's something that we almost arrived to already last time when we talked about autoencoders. So let me just briefly remind, right? That's an architecture that typically has some kind of a bottleneck, and it's a multi-layer neural network that has a x mu at the input and also x mu at the output. And last time we wrote the corresponding loss function, and the training, we just said that it's essentially always the same as for the usual feed-forward supervised neural network training. So here, for instance, we think of a fully connected layer. The layers could be different, right? And there is this, usually in the middle, there is a kind of bottleneck that is smaller dimensional than the input dimension and the width of the layers. And then this part is called encoder, and this part is called decoder. And we train the full autoencoder. So we first train the autoencoder. And then you cut at the bottleneck. And feed random noise to the decoder, and your output are close to samples, is close to samples. Right, so the idea is simple here. That's why at the end of last time we did this argument that if we train an autoencoder with narrow enough bottleneck, then what we in a sense achieved is an optimal compression of the data that we have. And if we had an optimal compression of the data, then indeed there should be absolutely no correlation between the variables in the bottleneck that represent that compression. And that's why this kind of second point makes sense, that we just cut at the bottleneck, feed random noise, because random noise is a vector that has no correlation. And the ways that we learned here, the idea is that the ways that we learned here in the decoder do the right thing, so that when we propagate the random noise from here to the output, we actually get something that is close to samples at the output. Okay, so that's a pretty basic idea how we do something like that using this idea of self-supervised learning and autoencoders and the kind of pipeline to train it. We take all of it from the supervised multilayer case that we discussed at length. So that's method 1. Another one that we will talk about that is very classical and kind of beautifully connects to things that you have seen in statistical mechanics if you have done it. It's called the Boltzmann machine. And some of you noticed that there is a section in the notes, the section about the Boltzmann machine is together with the unsupervised learning. But since this summer I was giving a lecture at a summer school in biological data processing, and when I was preparing the lecture, the way I wanted to explain the transformer architecture actually went through the Boltzmann machine. So that's why this year we actually shifted it to this lecture so that it kind of comes smoothly together. And so what is the idea there? The setting is the same, data and samples in d dimensions. But in a Boltzmann machine, what we focus on is we actually focus on the empirical means and correlations So from the data, we compute the empirical means. So for each element of the d-dimensional vector, we compute average of it over the samples. And similarly, we compute a covariance matrix that, again, is average over the samples. But this time, we correlate the position I and the position j, and we usually subtract here the means like that for this to have a zero mean. No, it doesn't have zero mean this way, but if they were independent, it would have zero mean this way. So from the data, we obtain the means and the covariances, and the covariance. And the idea of a Boltzmann machine, it searches for a probability distribution, P of x. So the idea here is search P of x so that the means and, how do I want to, all right, so search P of x so that some quantities, so, okay, I want the whole, okay, I want to introduce this so that, so some functions fa of our data of the x, and here x, here x is the d-dimensional vector. So those are samples from the probability distribution that we are searching for, so that functions fa have the corresponding mean. Okay, I'll leave it here. Meaning that the integral of fax with respect to the probability distribution that we are searching for, dx, is fixed to the empirical value. And in the Boltzmann machine, we care about the empirical mean and covariance. So this A is indexing all the constraints. So this A indexing all the constraints. So here we will have, from 1 to D, we will have the FAX that is just the mean. That is just XA. Could do it this way, XA. And for A, that is D plus 1 up to, so now, okay, I think here I need to write D plus D plus 1 over 2. Those are all the pairs, okay? So for those A's that are bigger, we just take X. Now, how do I want to write it? Sum. I will write sum. So this A actually is an index that gives me the indices sum K and L, and I will write K, L here. Right? So for each of these indices A, I'm just indexing all these constraints separately from 1 to whatever number I have of the means and the pairs. And each of these indices then gives me which index it corresponds to. So I'll write it this way. So I have the constraints that constrain the means and those that constrain the variances. And the important thing here is that the rest of what comes from the data I'm ignoring here. The Boltzmann machine only cares about the means and covariance and wants to find a probability distribution that has the same means and covariances. And how is this done? So this is done with something that we call the maximum entropy principle, that those of you who have done statistical physics are familiar with. You can basically derive all the statistical physics by saying, I write the entropy function, the Shannon entropy, and then I fix what is fixed by physical laws. So for instance, energy, by conservation of energy, I fix it. And then I just take the probability distribution that maximizes the entropy that derives the Boltzmann distribution, as you will kind of remind yourself in 5 minutes or so. Right, so the maximum entropy, meaning that I have a, okay, let me call it big H, not to confuse with the Hamiltonian, of a probability distribution is minus and sum over x's and log, let me write it this way, P of x log of P of x dx. Right, so this is the Shannon entropy that at least in EPFL is taught in the very first year in the ICC class, the kind of computational thinking, so you should have seen that already. And so we want to maximize this entropy, so we want to find P of x that for which this functional HP of x is the largest possible, but that is such that these empirical means that we measured, let me call them this way, empirical. So those are some numbers that we computed from the data, those ones, are actually equal to the corresponding integrals. So FAX, PX, dx. So how to do that? That's the way to do that. That's something that is actually very similar to, you have learned probably in analytical mechanics, you kind of exercise that a lot. How do you actually maximize functionals under external constraints? So constraint maximization. And you learn about the method of the Lagrange multipliers. So, who remembers about Lagrange multipliers? Hopefully most of you. If not, remind yourself. Yeah, I think most of you raised hands. And so what do you do there? You write a functional, the so-called Lagrangian, that will depend on what you want to optimize. That's your probability distribution, and will also depend on Lagrange parameters that here I will call gamma and lambda. And this will be the thing you want to maximize. And then you add here constraints. So one constraint is that your probability distribution actually needs to be normalized. And the other constraints are you have all the constraints from A to, okay, whatever is that, the total number of constraints. So I think it's D plus 1 over 2 of these FAs, of lambda A, the Lagrange multiplier, and then the constraint that needs to be satisfied. So the fact that the empirical mean needs to be equal to the mean over your distribution. So you have this. Now you want to maximize it. What do? You do derivatives with respect to the parameters, and you set them to 0. So for instance, this is equivalent to just saying that the constraint, this constraint, is indeed satisfied. And similarly for the lambda here, is 0, that's just equivalent to this other constraint being satisfied. Right? So this empirical is actually what it should be. Px, Fax, dx. So these two derivatives, they will just be ensuring that the lambda and gamma are set in such a way that these constraints are indeed satisfied. And then the derivative that is non-trivial is the one with respect to the probability distribution. So here, it may seem, if you haven't done derivatives with respect to functions for a bit, it may seem scary that we are actually deriving with respect to a function. This is a functional and this is a function, so indeed. But then it's actually, deriving with respect to functions is easy, since here we only have the function and not its derivative, so integrals is completely easy. We just do it in a way as if p was a variable and we were just deriving with respect to p. And this is also something that in analytical mechanics you have actually done when you wrote the Euler-Lagrange equations. For those of you who still remember that, that was exactly for the same reason, because you were deriving the action with respect to functions of positions and speeds that also depended on positions. So in a sense here, one can also think this is a baby Euler-Lagrange equation. I just set this to 0, and the derivative is the following. So what I need to write here is here I have minus. So if I derive the logarithm here with respect to p, it gives me 1 over p. So here I have minus 1. And the other term, if I actually derive the p and leave the derivative, I just have minus log of p. And the integral, I'm not writing it because everything in the integral needs to be equal to 0. So, okay, I should not be writing this. I should be writing, it follows that this quantity will be equal to 0. So that's by deriving this. By deriving this, I simply get the plus gamma. And by deriving this, I get sum over A, Fa of x. And here I get the lambda A as well. And that's it. And this needs to be equal to 0. So this needs to be equal to 0 follows from this derivative with respect to p. So I see that p is only here, so I can express it. So hence P of x needs to be equal, right? I put it on one side, needs to be equal then exponential of what? Gamma minus 1 plus the sum of these constraints, lambda a, right? And now this is the result. Okay. That's a generic form of the result. Now let's, before going back to our constraints and to the Boltzmann machine, let me just recall. Right? If we only have one constraint where this Fax is some kind of Hamiltonian of x, of the configuration, then x will be configuration of some physical system, and what we are fixing is the energy, is the Hamiltonian, then what is becoming this is just P of x. I call this e to the gamma minus 1, that's just a constant, so I call that constant 1 over z. And then up there I only have one constraint, I have e, okay, some plus lambda a, I have only one a, h of x. So if I set this lambda to equal to minus beta, which is minus the 1 over, in physics, kBt, minus the inverse temperature, this is exactly the Boltzmann distribution, right? That's how you derive the Boltzmann distribution. In statistical mechanics, you have one constraint. But now we will go back to fixing the means and the covariance. And if we do it this way, then the distribution that we get, right, we will call, then we get this. So again, there will be some normalization, right? The parameter gamma fixes the normalization. So this e to the gamma minus 1 is just 1 over the normalization. And that's how we will denote it. And then we have exponential and then sum over all the constraints. And so we have the constraints that depend on a single variable. Where did we write them? Down there, right? Fax is just xa. So those will be summing over all the possible components of our vector, xi. And there is the Lagrange parameter corresponding, the lambda. We will call it hi. So the lambdas, lambda a for a that is from 1 to d, we will call them hi, or ha, I guess, but then, okay, a goes from 1 to d, and here we just call it I. So that's on the side of the means. And on the side of the variances, we get similarly sum over all pairs, and then xi, xj. And here the Lagrange parameter, we will call it jij. Right, this comes from me plugging to this sum all those constraints that we explicited just above here. We have those that relate to just one variable and those that relate to a pair of variables. And the corresponding Lagrange parameters, the lambda a's for a that is from d plus 1 up to the last one, we just call them jij. Okay, so these are the Lagrange parameters. Lagrange parameters, and we must fix them in which way? We must fix them, well, so that, the empirical mean of xi, let me write it this way, empirical mean is the same as the mean of xi with respect to this probability distribution, and the same for the covariances. So the empirical must be the same as the measured one. Sorry, xi, xj, xi, xj over the probability distribution. So these constraints fix or imply the values of the j and h. So, and this form that we derived, right? At one hand, we recognize what this is. We already saw that previously because this is the Boltzmann distribution of the Ising model looks similar. Like this would be the magnetic field in in statistical physics, and these would be the interactions between particles, between spins in statistical physics. So in statistical physics, we usually think about this function as if, well, it's still a function of x, but we usually have the interactions and the magnetic fields fixed by the physics, right? They are somehow postulated, these are the interactions in our system. And here we are kind of doing the inverse. That's why the Boltzmann machine, so this is called this probability distribution is what's called the Boltzmann machine. And I mean, in general, when x are real valued, so we didn't restrict our x. But when x is actually binary, we can think of this. If the domain of our data was actually binary, we could think of this as an inverse Ising model, as the kind of system where we actually observe configurations from the Ising model. We don't know the interactions and the magnetic fields. We present you n samples from the equilibrium of that model. And from those samples, you actually should compute where the fields and the interactions. So that's why inverse, right? It's not that the fields and interactions are given and we are sampling. It's the inverse. We have the samples. And from the samples, we are inferring what actually were the fields and the interactions. So that is not something that we typically do in physics, but this is kind of so the Boltzmann machine is kind of the inverse Ising model, if you are familiar with the Ising model. And if you are not, never mind, right? From the backwards, it should be clear. So we arrive to that. So we arrive to that. So now we have a form of the probability distribution that we should seek so that we can constrain, so that we can keep those empirical means and those empirical variances. So now the only thing that remains is how do we algorithmically, so what is the algorithm? To actually find the values of these Lagrange parameters, to find the hi and the jij's. Right? We haven't said that yet. We just said kind of abstractly their values must be such that the empirical means are the right ones, but okay, how do we do that? So we will basically write two ways. So one of them will be, so when we stay in the real domain, so the real domain, when truly our x are real, and okay, let this be the matrix, n times d. Yeah. I mean, one needs to be careful on the blackboard. X is sometimes a matrix and sometimes a vector. I kind of did not really distinguish, but let me, how do we do that? If I underline, we usually underline. So this is the matrix. It's not often the matrix, only at the very beginning and here. In the rest of the blackboard, the x, when it doesn't have an index, is actually a kind of arbitrary d-dimensional vector that is a parameter of all these functions. It's not the matrix, right? When I, for instance, here integrate over x, I'm integrating over the d-dimensional space, not over all the matrices. So we stay in that real domain, and then actually, what we see, this probability distribution not only looks like the Ising model, but if x are binary, but if x are real, what is it? It's exponential to something quadratic. Right? There is all the binomials are there and all the monomials are there. So it's exponential to something quadratic. So we can actually complete the square in the exponential, which will, maybe it will change the constant. But if we complete the square, we can write it in this way. X minus some mean and some covariance minus 1, and x minus mean like this. right? In the sense that if we complete the square in the exponential, we get the Gaussian distribution. So this is just, we just realized this is just the multivariate Gaussian. What we wrote there is just the multivariate Gaussian. So we know that if we complete the square, we will get a form like that, where this is the d-dimensional vector, this is the d-dimensional mean, and this is the d times d covariance matrix that is inversed in the expression for the multivariate Gaussian. Okay, and this, okay, if we kind of do the matching, this gives us what should be actually the h. So at one hand we have that this is the mean, so this must be equal to the empirical mean, empirical. This is the covariance, so this must be equal to the empirical covariance, empirical. And then when we match kind of what is what, for instance, the term with x squared has a sigma inverse here and jij there. So this just gives us that j, and I think I changed also the sign, and the half. The half is here because here it's sum over everybody, and there I was summing over pairs. So unless I made a mistake, the half just doesn't appear. So what I get is that the j is just minus, because I changed the sign, the inverse of the empirical covariance. And similarly, the h, I just need to look what do I get here. If I look what is the linear term, I just get x times sigma inverse times mu twice. So the h will just be sigma inverse empirical mu empirical. Right? So this is not even an algorithm. This is just a concrete prescription from the empirical values that I computed up there. I just need to take inverse of the covariance, and those will be the j's. And I just need to take the inverse and multiply it with the mean, and those will be the h's. So I plug this in, and I have the probability distribution from which now I can sample and create samples. And how do I sample from such a probability distribution? Well, now I have a form for the probability distribution, so now I can use Monte Carlo to sample from it. Right? So I do that, and then I sample with Monte Carlo Markov chain, as we learned, for a given value of j and h that is given by the empirical means and covariances. Okay? So that's one way. And another way that is kind of are there questions about this one? Yeah, good. And then the other way is via maximum likelihood. That for the real domain becomes equivalent to just writing this multivariate Gaussian. But for instance, if we, for instance, constrained, this is in particular useful if the domain of X is not the real numbers, but for instance, just plus minus ones or binary variables. So this arrives, for instance, the kind of in my career, the first applications of this approach that I have seen were people that were actually modeling neurons spiking in the retina. And there the neuron either spikes or not. So the variables of the observations are binary. And then they actually wanted to infer what are the interactions in the retina from recording of the spikes. So they recorded many different spiking patterns. And from those spiking patterns, they wanted to reconstruct the probability distribution. So that's a case where these variables are binary. Another case that here, there are several groups in EPFL that in physics and in life sciences that widely use this approach to model the protein sequences. So what is actually the generative process that provides the protein sequences in our body that do something useful? So what they do, so in that case, they don't have only binary variable. In a protein, each site has one of the 20 or or the 20 amino acids. So actually, which amino acids is there? It's one of 20 variables. So it's not a Ising model. In physics, we call this a Potts model when we have actually several values of the spins. But again, the values are discrete. It's one of the 20 amino acids. So this kind of approach where X needs to be real values to be able to kind of write this multivariate Gaussian does not apply. So one just looks at the maximum likelihood, meaning what? Meaning that one writes the likelihood of the data, of the observed data, so one takes the form of the probability distribution right here and makes a product over all the samples that one observed, P of X, right? This is parameterized by the H and J that we don't know their value yet, that we are looking for. So you will be looking at it as a likelihood that is function of H and J. And then we are maximizing over, maximize this over H and J. Right, so now we are in a kind of, again, in a familiar ground. We have a loss function, and now we are, okay, this time not minimizing, but maximizing, but never mind. I could have just, if I define this logarithm of this with the minus, I would have been minimizing. But okay, maximizing, minimizing, you can like each figure out which one. We were never checking whether our setting derivatives to 0, whether it's actually a minimum or a maximum. It always worked the way that we were kind of stating it. And the same here, because this actually ends up a convex function, so it has a unique stationary point, and in this case, it's a maximizer. But let's write then what are the derivatives, right? So that's a familiar ground because we know in principle how to solve such maximizations. We just have the gradient descent for this. And if we actually, I will not do it in detail, in the notes you have it in detail, if we actually write the derivative, right, put this form in, make the derivative with respect to H and J, and write what gradient descent is, we will just get the following update equations. You will see that they are very intuitive. This is gamma, the learning rate. Okay, sorry, I should, okay, let me call it mu, since gamma we already had today. The learning rate. And then what remains from the derivative is actually a difference between the empirical average and the current average with respect to the current H and J that we have. So if I should add here indices, this would be the T. And similarly for the Jij, T plus 1 will be the Jij in the previous time step of the gradient descent plus learning rate, and here I'm putting a correlation, the empirical one, minus the one with respect to the probability distribution at the previous H and the previous J, like this. Right? So, for instance, if the empirical mean is still bigger than the current mean with respect to the distribution with respect to the current position of H and J, then, well, we should set H so that the mean becomes bigger. So the learning rate is positive, and indeed we will be adding here a little thing to the current H. And we will be doing it as long as the empirical mean is actually equal to the mean over the distribution. When they're equal, this term is 0, and this is where the gradient descent will stop converging. Right? So this actually, this final form is very natural, so that's why I kind of say we can skip the derivation, because it comes in a form that indeed, at the convergence of gradient descent, the constraints that we wanted to be satisfied will be satisfied because the terms in the brackets will be 0, and that's exactly what we wanted. So the way you train Boltzmann machine if you're on an arbitrary domain is with a gradient descent. And last thing, one thing I didn't say yet, right? So this we know, this we observed, so this is a number that we computed. How do we compute these means with respect to the probability distribution? with the current values of h and j? Well, again, with Monte Carlo Markov chains, right? We have a current value, and we want to sample x and compute the averages of x. That's exactly what was the point when we learned about the Monte Carlo Markov chains. And here is just the observable is different, is the product of two variables and not only one. So this is kind of a nice example because the two kind of landmark algorithms that we learned about in this class, the gradient descent and the Monte Carlo Markov chains, that get combined in the same pipeline, right? We need the Monte Carlo to be computing these trial averages, and we did the gradient descent to be updating our parameters. And then we update them, then we run the Monte Carlo for the yet new ones and iterate this way. So that's kind of a nice algorithm. Okay, so then there are versions of the Boltzmann machine where you add hidden variables such as the restricted Boltzmann machine and de-Boltzmann machine, but I decided kind of not to dwell on that in this lecture because these days they are kind of not so much used. Rather, we will go to the methods that are kind of driving the development these days. And the way we will explain them after the break is basically with a similar spirit, but now realizing that there is a problem with what we did here. Right? The problem with what we did here is at the very beginning, when I started method 2, we fixed the means and the covariances. But there is more in the data than the means and the covariances. Why did we focus so much only on the means and covariances? So this is indeed what is often done, and the kind of formula of the Boltzmann machine is derived from that by maximizing the entropy. But if there is more kind of information in the correlations between the data than the means and the covariances, then we completely missed it. So we will, after the break, describe a method that actually does not only aim at fixing the means and the covariances, but tries to kind of work with the data as a whole. And it's a method that existed for a while around for this inverse Ising model. So it was an alternative way to actually solve this inverse Ising model. And especially in the statistical physics literature, there are dozens of papers on that. It was called pseudo-likelihood. I really don't like the name is strange. I mean, there is nothing much with it with likelihood, but it's an alternative of finding these. Of finding a way to generate x's from samples of x's that kind of circumvents this restrictive idea of fixing only the means and covariances. So we will describe that after the break, and then what kind of it gives us, it's something that has been around for a while, but there was a beautiful paper actually about a half year ago of colleagues who linked this method to the concept of the attention layer. And so that's how we will come then to the attention layer and then describe the actual attention layer that is used in transformers after the break. But let's see in a bit.